Here we have a very comprehensive table of the four thermodynamic processes that we're going to look at: the isobaric process, the isochoric process, isothermal, and adiabatic. But before we even look at these processes, we have to think about something else. There's something that we are all familiar with, and that is the ideal gas law. The ideal gas law says that at any state, PV equals nRT. So here, P is pressure, V is volume, N is a number of moles, R is the ideal gas constant, and T is temperature. Another thing that we have to pay attention to is that in physics, P is measured in pascals, V in cubic meters, temperature in Kelvin. So we need to convert units in case they're not the correct units. So if at an initial state, P initial, V initial equals nRT initial, and then the same system will end up in a final state, P final, V final equals nRT final, then we know that it's an isolated system, so the nR will stay constant. So if we just solve for nR in both of those equations, we end up with P initial, V initial over T initial, and that's the same as P final, V final over T final. So this is a very good reference equation when we go between two states. So if the system starts in state 1, it has a particular set of pressure, volume, and temperature, and it ends up at state 2 with a particular set of pressure, volume, and temperature. All right, now let's think about another concept, and we talked about this in an earlier lecture as well, and that concept is the concept of work. So we said that work was pressure times change in volume, and we also said that on a PV diagram, the area under the curve was the work. We looked at work as the area under the curve for this equation as well. Force times dotted into the displacement. So it's a similar concept. Now, let's start looking at our particular processes. So first, we have the isobaric process. Iso means the same. Baric comes from pressure, so this means same pressure. So the pressure throughout this process is going to be constant. So here we have the system starting at initial pressure and ending up at a final pressure, and that is the same. So now if I want to find the work, all I have to do is find the area under the curve, and that will give me the work. Now, if we look at the equation that we list here for work as P times delta V is V final minus V initial. So looking back at the isobaric process, V final is higher than or larger than V initial. So in this situation, work is greater than 0. So we have positive work. But if we had a situation in which the initial volume was larger than the final volume, and this is not an isobaric process because I didn't draw the line to be parallel to the v-axis. But if we have the final volume being less than the initial volume, then the area under the curve would be the work, but it would be less than 0. So what this says is that in this situation, work is done by the system, and in this situation, work is done on the system. So work is negative. If we look next at the isochoric process, so iso means the same, choric comes from volume, so it's the same volume, V is constant. So V initial and V final are the same. If we look at the equation for the work, delta V is going to be 0. So that means that the work for an isochoric process is just 0. For the isothermal process, work again is the area under the curve. So to find the area for this type of curve, we would have to take an integral. And when we do take the integral, we end up with work being equal to the number of moles times the gas constant times the temperature, that constant temperature that the isothermal process will have, times log of final volume divided by initial volume. Again, if this arrow, if the process were going in this direction, then the work would be positive. So that would mean that the system does work, not that the work is done on the system. The arrow would have to go in the opposite direction for work to be done on the system. We will look at the adiabatic process a little bit later because it's different than all the others. For the isobaric, isochoric, and isothermal, one of the three quantities here, P, V, or T, is constant. For the adiabatic process, we have Q being equal to 0, but none of the pressure, volume, and temperature are constant. So let's look at the change in internal energy. It is the same for all processes. So the change in internal energy is N times CV times delta T. CV is specific heat at constant volume, and it's given by 3/2 R for a monatomic gas. So the change in internal energy is the number of moles times specific heat capacity at constant volume times the change in temperature. So that's the same for all processes, but for the isothermal process, since delta T is 0, then the change in internal energy is also 0. The next quantity is the heat, and in most cases we're going to solve for it by using the first law of thermodynamics. So heat is change in internal energy plus work. So let's look at the isobaric process. Q is work plus change in internal energy, so that would be P delta V plus NCV delta T. So from the ideal gas law, from over here, PV equals nRT, that means that P delta V is equal to nR delta T, because P is constant. So then nR delta T plus NCV delta T is equal to Q. And then if we look over here, we see that Cp is Cv plus R. So Cp is specific heat capacity at constant pressure. And looking at this value here for a monatomic gas, Cp is 5/2 R. So in that equation, I'm going to factor out N delta T. So I have N delta T times R plus Cv, which happens to be Cp. So heat for the isobaric process is NCP delta T, and this is really the only place we use Cp. All right, for the isochoric process, heat again is change in internal energy plus work. So it's the sum of the work, which is 0, and change in internal energy, which means that the heat in an isochoric process is NCV delta T as well. For an isothermal process, heat is work plus change in internal energy, so we get nRT natural log of V final over V initial, and I wrote work here. I was supposed to write heat, so I guess I'll say Q equals work, and they are both nRT natural log V final over V initial. Now, let's look at the adiabatic process. So, adiabatic means again that heat is zero. That does not mean that temperature is constant. Temperature, pressure, and volume, all three of these quantities change, but the heat exchange is zero. So we have a special equation that relates the different states, initial and final states, and that is P initial, V initial, and V is to the power gamma equals P final times V final to the power gamma. Well, this gamma is the ratio of specific heat capacity at constant pressure divided by specific heat capacity at constant volume. So for a monatomic gas, gamma will be 5/2 R divided by 3/2 R, so gamma is just 5/3. So this is the only time we're using this equation for the adiabatic process. Now, we know that the heat exchange is zero, and we also know that for all processes, the change in internal energy is NCV delta T. So we can use the the first law of thermodynamics, to solve for the work, and that will be Q minus change in internal energy, which is 0 minus NCV delta T, so work is going to be negative NCV delta T. And that way we don't have to actually find the area under the curve. We don't have to do the integral to figure out what the area under the curve is for the adiabatic process. So there are some similarities and differences between these processes. For the isochoric, isothermal, and adiabatic process, one of the three types of energy, work, change in internal energy, or heat, is zero. The isobaric process is the only one that has non-zero work, change in internal energy, and heat. The isobaric process is also the only one that uses NCP delta T. So there are a few similarities and a few very distinct differences between these processes, besides the whole concept of one has constant pressure, one has constant volume, one has constant temperature, and one has no heat exchanged. And it is fairly easy to remember the unique situation for each of these processes.